Hello everyone. Today in this physics concept session we are going to discuss semiconductor devices along with communication systems. Semiconductor devices lesson contains classification of metals, conductors, semiconductors, intrinsic semiconductor, extrinsic semiconductor, PN junction diode, and semiconductor diode, applications of junction diode and transistor, etc. Of course, logic gates also. Conductors. Conduction band and valence band overlap in conductors. Conduction band, valence band overlap in conductors. Semiconductors energy gap is very small, but they are separated. Silicon energy gap is 0.72 electron volt, whereas germanium is 0.34 electron volts. And current due to electrons and holes will cause us net electric current, and current due to electrons is NEA VE. VE is drift velocity, and NEA VH. VH is drift velocity of holes. Intrinsic semiconductor. Intrinsic semiconductor. Pure semiconductors are known as intrinsic semiconductors. Number of free electrons Ne and number of holes NH both will be equal in number in pure semiconductors. For temperature, if you change, then intrinsic semiconductors mobility or conductivity increases. That is, see, Nt is equal to N0 e to the power of minus Eq by 2 kBt. Kb is Boltzmann's constant and remaining things are as usual. T is temperature, Eq is energy gap, and N0 number of free particles, whatever electrons or holes. Of course, holes are not materialized particles, a concept of absence of electrons. And Fermi energy level lies exactly at the middle of the forbidden band, that is pure semiconductor. P-type semiconductor, in which number of holes are greater in number, number of holes are more in number, in such a way doping is done. Extra number of holes are more, so extra holes, so intravalent impurity is doped, intravalent impurity is doped, and Fermi energy level is close to, holes always will be in the valence band, so close to valence band. Next, Ni is general mobile charge carrier concentration, Ni. Ne and NH are electron concentration, hole concentration. So Ni square equal to Ne or Ne into NH. Here dot is, it is taking as a statement. 1 minute. Yeah. Actually Ne into NH is equal to Ni square. N-type semiconductors, Ne greater than NH. Electrons more in number in N-type semiconductor. In Fermi energy level, conductivity of semiconductors is sigma is equal to E into NH mu H. Mu is nothing but mobility, Ne mu E. Potential difference across the depletion layer for silicon is 0.7 volts and 0.3 volt for germanium. If V is the barrier potential and D is the thickness, then field developed across the depletion region is V by D, which is an order of 10 to the power of 5 electron volts. And here are dynamic resistance, because semiconductor devices are not having fixed resistance, they have dynamic resistance. R is equal to delta V by delta I. Rectifier. Rectifier is a device which converts AC into DC, alternating current into direct current. Half wave rectifier, it converts half cycle of applied AC into DC, output frequency is N only. Efficiency of half wave rectifier is eta is equal to DC output by AC input, and its expression is given by 0.406 RL by RL plus RF. This is efficiency of half wave rectifier. Full wave rectifier. Full wave rectifier contains 2 diodes, but at a time one diode only will be action in conventional rectifier. Of course, many types of rectifiers are there. It converts whole cycle of AC input into DC output, and its frequency will be 2n Hz. Of course, that variation can be removed using filters. Efficiency eta is equal to 0.812 RL by RL plus RF. Zener diode. Heavily doped PN junction diode is known as Zener diode. Heavily doped PN junction diode. It's also junction diode only in forward bias. In reverse bias only, its action is different. It will have sharp breakdown in reverse biasing. And this PN junction diode also having dynamic resistance, but it tries to maintain always its terminals at same potential difference. So current through the load resistance IL is equal to V0 by RL, that is VZ by RL. VZ and V0 will be equal because resistance is always taken parallel to the diode, so that diode terminal resistance only will be diode terminal potential difference only applied to resistance. So potential difference across resistance and diode will be same. That's why V0 is equal to Vz. Voltage across series resistance V is equal to Vin minus Vz. Voltage across series resistance V is equal to Vin minus Vz. Now current through Zener diode is Iz is equal to I minus IL. LED, light emitting diode. It's a heavily doped PN junction diode under forward bias, which is LED, light emitting diode. And then it is basically a PN junction which is under no external biasing. Which one? Solar cell. No external biasing. IV characteristics of solar cell is like this. Intensity or current it is, and V is the potential difference. Then the graph will come like this. Transistors are of two types. See, if the arrow mark is towards the base, this is PNP transistor. If arrow mark is out of the base, then NPN transistor. This is PNP, this is NPN. Next, any transistor circuit IE is equal to IB plus IC. For any transistor, emitter current is equal to base current plus collector current. And change in IE will be definitely equal to change in IB plus change in IC. Usually base is lightly doped, so base current is lesser than emitter current. Emitter current always greater. That only divided into base and collector. This is common base configuration. Base is common for the both input output terminals. This is common emitter configuration. Emitter is common for the both input and output. In common base configuration, current gain is output collector current, input emitter current, IC by IE. This is alpha, always less than 1. Then in common emitter configuration, current gain is beta. Current gain, beta, not alpha. I will write with the pen only. I don't want to change it. This is not, this is just beta. Actually, this is alpha. Alpha is equal to, okay, IC by IB. Here output is IC, input is IB. That's why it's always greater than 1. A correctly doped PN junction diode will have 20 to 200 beta value for current gain. And voltage gain will be voltage gain, output voltage by input voltage. Output is VCB by VBB. VCB by VBB. And IC, that is equal to voltage gain equal to IR. So current gain into resistance gain. Resistance gain is RL by RI, or beta into RL by RI. RL means load resistance, RI means input resistance. And power gain is equal to power gain, AP is equal to, you can write current gain into voltage gain, or current gain square into resistance gain, that is I square R. Or so output power by input power change. Relation between alpha and beta is alpha equal to beta by 1 plus beta, because alpha always should come less than 1, or beta equal to alpha by 1 minus alpha. Beta must be always greater than 1. These two are very, very important. Feedback amplifiers. It returns a fraction of output voltage back to the input, which is called feedback amplification. Resultant gain of amplifier with feedback. AF is equal to output voltage by input signal voltage, and AF is equal to A by 1 minus A beta. Positive feedback, AF is equal to 1 by 1 plus A beta. 1 plus A beta. And beta is the feedback fraction, beta equal to Vf by V0, and A is equal to V0 by Vi. The condition A beta is equal to 1 is called Bragg-Hahn condition for oscillations. The efficiency of oscillation F equal to 1 by 2 pi root LC only. Logic gates. OR gate, addition. OR gate is nothing but addition gate. Y equal to A plus B, this is circuit symbol. And inputs are 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1 in this. If any one is 1, output will be 1. And this is theoretical semiconductor circuit, electronic circuit we can call it as. Next. AND gate symbol is like this. If both are 1, then only 1 you can get. If both are 1, then only 1. And circuit symbol will be, electronic circuit will be like this. Circuit symbol is the first one. Next. NOT gate. NOT gate means just like a negation. That means if I say 0, you need to say 1, like that. Always student will say opposite. That's what. And input is A, output is 1. If here one more I can write. If input is 1, then output can be 0. And NOT gate can't be constructed with diodes. NOT gate definitely needs transistor. NOT gate, R plus NOT gate. NOT gate is this one. This is NOR gate. NOR means R plus NOT. NOR gate. NOR. R plus NOT. So output of R gate should be given to a NOT. So output of R is any one is 1. Right? Here any one is 0, the other one is 1. And NAND gate will be there. NAND NAND. Output of AND gate is given to NOT. So AND plus NOT gate. NOT. NAND gate it is. In NAND gate, output is given what you call AND gate. If both are 1, then only 1. Here both are 1, it will be 0. Just reverse. Next, Boolean algebra. A plus 0 always A plus 1 always 1. A can be whatever, either 0 or 1. A plus A is equal to A plus A is equal to A, and A dot 0 is 0, A dot 1 is A dot A is A, and A plus B whole bar, De Morgan's law, A plus B whole bar, A bar dot B bar, A dot B whole bar, A bar plus B bar, A bar plus B bar whole bar, that is A bar dot B bar whole bar, A dot B. And so NAND and NOR gates are called universal gates. With them any gate can be constructed. XOR gate, AB bar plus A bar B, that is XOR gate. This gate contains, if both are having same type of inputs, then it will give you 0, different inputs, then 1 will come. Output becomes only 1 when inputs are unequal. XNOR gate, reverse. XNOR gate is reverse. Yeah. NAND gate as NOT gate, just give the combined input for A and B. And NOT gate also, NOR gate also NOT gate, combine the two inputs and give to what you call diode. Communication systems. Basic blocks of communication system. Modulation, channels. These things we are going to discuss in this chapter. They are: speech signals are 300 to 3100 Hz, bandwidth of 2800 Hz. Video signals require bandwidth of 4.2 MHz for picture transmission. However, a bandwidth of 6 MHz is needed for TV signals. Wireless communication frequency bands. These are our wireless communication frequency bands. At least few you have to memorize, remaining things not required. Ground wave propagation. To radiate signals with high frequency, antenna should have a size comparable to the wavelength or at least lambda by 4. Ground wave propagation suitable up to 2 MHz. Otherwise, very high sized antenna is needed. Skywave propagation about 2 MHz to 30 MHz. We are going to use skywave propagation for long distance communications, and it use the layers of ionosphere by reflecting them, as whenever the ray moves from denser medium to rarer medium takes total internal reflection. That concept only used in skywave propagation. Another one is space wave propagation, which is direct straight line propagation for communicating with satellites and all. The space waves are used for line of sight LOS communication, frequencies of 40 MHz. If the transmitting antenna is at a height ht, then distance to the horizon dt is equal to square root of 2r ht. This is what distance horizontally can be transmitted using this much of height of the antenna, that is square root of 2rh, like 2gh, instead of g you have to take r. And if both the antennas are used, that means receiving antenna and transmitting antenna of different heights are used, then total distance of communication is square root of 2rhs plus 2rhr, receiving and sending. Number of persons covering by transmitting power is equal to area covered by the tower into population density. Power radiated by linear antenna is always proportional to L by lambda whole square. Amplitude modulation. Amplitude of the carrier wave is varied in accordance with the information signal. Let carrier wave is C of t AC sin omega ct, carrier wave configuration, and message wave configuration is AM sin omega mt. If both are modulated, that means overlapped, then it is going to take up a form AC of 1 plus mu sin omega mt sin omega ct, where mu is known as modulation index. Modulation index is equal to AM by AC, that is A maximum minus A minimum by A max plus A minimum. These are all in voltages actually. Okay, next. If carrier wave is modulated with too many message signals, then with different modulation indices mu1, mu2, mu3, net modulation index of the modulated wave is given by square root of mu1 square plus mu2 square and so on. AM wave contains three possible frequencies: FC minus FM, FC, FC plus FM. And bandwidth is the frequencies of lower sideband and upper sidebands. FC minus FM, FC plus FM. The bandwidth is the frequency in between these two ranges. That's obviously 2 times of FM. And power of the carrier wave is given by AC square by 2R, where R is the load resistance. Power of sidebands PS is equal to mu square AC square by 4R, that is equal to PC mu square by 2. The total power of AM wave is P is equal to PC plus PS, which is AC square by 2R of 1 plus mu square by 2. Fractional power carried by sidebands is PS by P equal to mu square by 2 plus mu square. Fractional power carried by carrier wave is PC by P, that is 2 by 2 plus mu square. And number of AM stations that can be accommodated in a wire is total bandwidth by bandwidth of each station. And frequency modulation index MF is F minus FC by FM. And the frequency of modulated wave so and so. C naught, velocity of the wave, is 1 by square root of mu naught epsilon naught in free space, and in a medium square root of mu m epsilon m. That is the medium characteristic. And next, these things related numerical problems we'll discuss in the subsequent sessions.